we'll look at one of the problems. Like yesterday we saw that the result that we are looking for should have a monotone, should be a monotone, like the function should be monotonic, right? This function should be monotonic. So we're going to see if it is, what if this function is not monotonic, but it is like the array that is given to us, it is of some different kind. Like it's not a U-shaped. If it would have been U-shaped, we would have applied ternary search, but it is something kind of zigzag. So how to solve, like if the pattern is of this type, so how to solve problem of this kind? Then we are going to look at, like if you remember yesterday, I told you something about advanced binary search, and the use of this is writing your own square root function. So we are going to look at this. This is easy, but still we are going to look at this because in many times due to precision you get error. So we are going to look at square root, and quickly we are going to also go over cube root. Then after this, we are going to cover advanced binary search plus ternary search. We are going to solve problems on this today. I'm not going to go into theory, like we'll go a little theory, but I think I have given you the introduction yesterday only. So I'm just going to recap at once. We are going to look at a little bit of theory. And since we didn't solve any problem on ternary search yesterday, we are going to solve hard problem on this today. Then we are going to look at interactive problems, and we only had one problem. That was a basic problem, right? So today we are going to solve around 2 to 3 problems on this, and these problems will be hard. And lastly, we are going to solve a problem which is going to be interactive. Like last 2 problems we'll try to solve, which will be interactive plus advanced binary search, and are having a concepts of ternary search involved in them. So this will cover everything that you should know in binary search. So this is our goal today. This is what we're going to follow. So let's start.
Sorry to interrupt you, but ये इसके पहले भी कोई क्लास हुई थी क्या बाइनरी सर्च पे?
Yes. I think like we had a class yesterday, right?
Oh, I was not aware of that. Sorry, but
So
the recording नहीं आया है.
yeah, I'll ask. Okay, the recording is still not available on the net.
No, I couldn't find it on the website.
Okay, some students are saying it's there. So kindly look it again, and maybe it was uploaded like today only. It was not. Maybe it was not uploaded yesterday, but you can look at it. And
Okay.
I have covered everything there. Like I have covered the complete binary search thing there. I have given an idea about what advanced binary search is. I have given an idea what ternary search is. I've given an idea what interactive problem is. We have solved around 4 or 5 problems there, and we have solved problems on interactive search. We didn't solve any problem with ternary, but we solved some hard problems on binary search. And then I think we also looked at some cases which are general mistakes that we tend to make during binary search, like while we are applying binary search. So you can go through it once, but it's okay. I'm trying, like, I won't cover those things today, but still you can like look like you can be in today's class.
Okay.
Like, you won't find that much like things like, because I'll start from basic only, but I won't go that much in deep today. So let's start with one of the problems. So let's quickly recap, and we'll recap using one of the good problems that we were not able to do yesterday. Like, okay, let me open that problem. Give me a minute. Okay, so the problem is, suppose that you have to find how many, like you have to find the smallest number for which, okay, I'll share the link also. But this problem is from GFG, and okay, but anyways, I'll share the problem also. So this shared it in the chat. So the problem is not from the code forces, it's from the GFG platform. So we have to find the smallest number for which the factorial, let's say the number is x, for which the factorial of x, like you may write it like this also, the factorial of this thing is having at least some n zeros. So how to solve this problem? We have to find the number n for which there are at least n trailing zeros at the end. First of all, like, is any like, if anyone wants to say something, you can say right now. Like, you can unmute yourself. Okay, I'll start. So n is less than or equal to 10 to the power 4. So yesterday we discussed that. See, first of all, when you're, see, this thing is clear to everyone, right? We have to write while, we have to write something low, less than, equals to high. We'll find the mid. Mid is nothing but low plus high by 2. Now, if there's a function here, function, and this is the most important thing, like, this is the, like, other than this, everything is generic template, right? You'll write this everything. So this function mid, and now if this mid is true, my answer is going to be at least this mid, and I can shift my high to mid minus 1. Otherwise, I'll change my low to mid plus 1. So this is clear to everyone, but how to write this function? What should go inside this function? Can anyone tell me how to check?
We can think of it as like a greedy function that gives a solution for a particular value that calculates over all the
Yes,
elements of the array.
yes. So basically, what we just need, first of all, we'll see how many numbers are having at least one factor of 5. Why? If, let's say, 3 numbers are having a factor of 5, we can always make 10 out of these. Why? Because 3 numbers are having factor of 5, then there will be at least 3 numbers which are having multiple factors of 2. Why? Because 2, you first have 2, 3, 4. In factorial of n, you have this thing, right? 1, 2, 3, 4, 5, 6, 7, 8. So basically 2 is, you get 2 many more times than 5. So for this, for just check how many times you're getting 5. So you just do, if n is the number till which you are checking, so do n divided by 5. N divided by 5, you'll get these many multiples of 5, and just add this to your number of zeros. Like, these are the zeros that you'll get. Now look how many times you're getting 25, because 25 will get 2 multiples of 5. One you have accounted for, but what about the other? So for this other also, you can just look at, see, for these 25 also, you just need to check how many times your number is divisible by 25, right? So once this is done, like, you'll keep doing this, n divided by 25. Next will be 625, right? While n is more than these multiples of 5. So you'll add all of these to your zeros variable, and finally you can check if zeros is more than the number of trailing zeros that you want. So you'll return true, otherwise you will return false. Is it okay? Like, is someone having any doubt in this? Okay, you can unmute yourself and let me know. Okay, I'll explain this again. See, factorial of n is nothing but 1 multiplied by 2 multiplied by 3 all the way up till n, right? So in this, you'll get some 5s. So 5 is more rare than 2s, right? The number of factors that you get for 2. So I'm just saying, first, see, for all the 5s that you're getting, you'll at least get 1, 2. So you can multiply this 5 with this 2, and you'll get a 10. So just count how many times you'll get a number which is having a 5 as a factor. So that is nothing but n divided by 5. All these numbers will have 5 as a factor, right? Yes, no, anything? So now some numbers will have 5 as a factor 2 times. So for all those numbers, you have, like, considered this one 5, but what about this other 5? So for that, you'll have to check how many times n is divisible by 25. Then you'll have to check n divisible by 625, not 625, 125. Then n divided by 625. So this is for 5 cube, this is for 5 to the power 4. So you keep doing this while n is more than this thing that you are dividing by. Finally, you add this everything to your zeros variable, that is the zeros that you're getting. If zeros is more than the number of trailing zeros, that is n, then you'll return true, otherwise you'll return false. And first of all, okay, everything is clear, but first of all, tell me why we can apply binary search on this. Okay, if you remember from yesterday, if our function, our solution function that we are applying binary search on should be monotone. So is this function really a monotone? Yes, it is. Why? Because if there are, let's say, some x zeros up till n, for n plus 1, you will have these zeros at least, right? It's not possible that the number of zeros will decrease. Why? Because n plus 1 factorial is nothing but n factorial into n plus 1. So all the zeros that you received in this part will also be a part of this number. Is it okay? Okay, so I'll quickly show you the code. This was just for like quickly revising what we learned yesterday. So yeah, this is the implementation. Okay, so this is the, just give me a minute. No, this is not the implementation. Let me copy my implementation once. Okay, I'm not logged in. Okay, yes, I'm logged in. Okay, so this is visible to you, right? So what we are doing, you have to find up till n. So what we are doing, if n is equals to 1, we have to return 5. Why? Because up 5 factorial is having 1 trailing 0. Other than that, see, if you are doing 4 factorial, 2 factorial, 3 factorial, you won't get trailing zeros. So if you want just 1 trailing 0, you'll have to return 5. Now you can do the 0 and high as 5 into n. See, up till 5 into n, you'll always get n zeros. But if you are not sure of this, like I said yesterday, I explained this in detail, you can assume this to be 1e9. But it isn't required here. Why? This isn't required. 1e9 isn't actually required here because why to increase your range like unnecessarily? But you can do it. So then binary search, this is the formula that, like, this is the basic template, right, for binary search. Finally, we are returning. So what is happening here? For check, we are just checking how many times it's divisible by first 5, then 25, up all the way up till x is less than this temp. So this temp is the original p that we are checking for right now. And n is the number of trailing zeros that we want. And p is the number up to which we will take our factorial. So this is okay, right? This is clear to everyone?
Can you tell why we have taken high as 5 into 9?
What can you just repeat yourself?
So why we have taken the high as 5 into 9?
Okay, like I said, if you want n zeros at the end, if you want n zeros at the end, if you the upper limit, if you take the 5 factorial of this thing, you'll have at least n zeros. Why? Because 5 is coming at least n times in this. If you will divide this by, like, just divide 5n by 5, you'll get n, right? Forget about 25, 125, 625. We are dividing by all of these also, but divide this number just by 5 and you'll get n zeros itself here. So there are at least n numbers which have a multiple of 5, a factor 5 in them, up till 5n, right? There are at least n numbers that have a factor of 5 if you're looking up till 5n, right?
Yes, sir.
So that's why. Like this is just one of the upper bounds. You can take the upper bound anything. Like you can be more precise than this sometimes, but you can, like, generally this will work. And even if you take something bigger than this, it should also work. So now let's move ahead, and now we'll start with looking at that thing. If our function is not monotone, like sometimes you will be given, if, like, let's say this is one of the most frequently asked problems during an interview. Suppose you are given a rotated sorted array and you have to find the maximum. So how, in rotated sorted array, you have to find the position of maximum element. So how will you do this? So position of maximum element. So what is a rotated sorted array? You first sort your array. Let's say 1, 2, 3, 7, 9, 11, 13, 20. And then you rotate it sometimes. So by rotation, we mean that these elements will shift in right towards direction, and this element, the last element, will come to the first place. And you don't know how many times this is done. So how will you solve this problem? Like, let's suppose you are given this thing, 1, 2, 3, 7, 9, and maybe 11, 13, and 20 are here. 11, 13, and 20. How will you solve this? How will you find the maximum?
what do we need to find here?
The position of the maximum element, that is this thing. Any idea? Like you already know this.
We will compare start, mid, and high. Let's suppose we will check if start is less than mid and high is greater than mid. So means the both line are opposite side of the rotated array. And then we will figure out which one is the right part, means which one is increasing. And for that one, we will apply if we will able to find out the number which is less than, then we will shift our start to mid plus one.
So basically, see, if you want to apply turn research, like I explained yesterday, it is applied on a function which is kind of this, right? U functions. But if you draw what this function might look like, sometimes you might see this thing. Because when I'm saying rotated, it's possible that it's rotated by 0 times, and sometimes you might see something like this, right? But the key idea here is you'll always see something like this. See, the maximum element that is going to be after that element, just after that, you're going to have the least element. The key point is this: always, if this is the maximum element, then the least, that is the minimum element, is going to be right next to it. Otherwise, this is your maximum element. If this is not happening, is anyone having any doubt regarding this part?
Okay, array will be rotated once or many times.
We don't know how many times it will get rotated. It can be rotated once, it can be rotated 0 times, it can be rotated many times.
So how it is always before the smallest element, the maximum element?
How? See, okay, I'll draw this. Suppose this is the 0 times when the array is rotated. Now I'll rotate it once, so the maximum element is here. After this, the value drops, and the rest of the elements are like this. So this is when I rotated 1 time. Then I'll rotate it twice. So now the second last element is this, the biggest element is this. Now the values drop, and the rest of the values are like this. So you're getting my point, right? If you rotate it one more time, this element will come here. So you'll have something like this, as I'll keep increasing my number of rotations. Is it okay? Who asked me this? Is it clear to that person?
Yes, I got it.
Okay. So now tell me, how will you solve this after looking at this thing?
Can we use the property that the largest element will be the largest among the previous and the ahead element?
See, now the problem is really easy.
First figure out the increasing part, which one is sorted, and then we apply the binaries, means that one here.
See, okay, I'll tell you. See, the maximum element is the only element whose next element is smaller than it. Other than that, there is no other element which is having the next element smaller than it, right? And in case if there is no element such that the next element is smaller than it, then we know already that there is no rotation. So the last element by default is the maximum. Now, how to check this? See, first of all, we'll find the mid, and then we'll check this thing using mid minus 1 and mid plus 1. We'll check for these two values. If maximum element is not in the middle, then neither mid and not the mid plus 1. Like if the element is not one of these, it's not mid and mid plus 1, then maximum element lies somewhere in either left half or right half. See, if this is the value, this is your arrays. If you do mid here and you check your mid plus 1, both of these elements are not your maximum. How will you check this? That none of the elements next to them is smaller. So you know that either the maximum will be in this part or this part. Same thing here, right? If I take my mid here, now mid plus 1 is this. But now how to actually shift my range? See, if middle element is greater than the last element, if this middle element is more than the last element, then the maximum element lies in the left half. Otherwise, maximum is always in the right half. Can we divide it into 2 parts and apply? Can you please explain this? As it is a monotonic function. Okay, like what do you mean by this, that dividing it into 2 parts and apply BS? How will you divide? Like you don't actually know how many times the array is rotated, right? You can just unmute yourself and...
I was thinking to divide it via mid and then applying binary search on individually on both of them.
No. Actually, for that you'll have to know, right? Where will you divide? If you divide randomly, maybe one part will have this thing and the other part will have this thing. So then this problem is again that initial problem only.
First, we find the pivot element in the array, and then we divide it.
So, but if you have found this element, you are calling this element as your pivot, right?
No, the smallest element as the pivot.
Okay, if this is your pivot, so by default you have found your answer only.
not a pivot element, index of a pivot element, and we can apply before the
If
index
you
of
found
the
the index, if you found the index of your pivot element, then your answer is A of pivot minus 1. If pivot is your index.
we have to
If you have found this thing itself, then your answer is this, right? So finding this itself is our task. And in order to find this, you have to apply binary search, like assume mid and check that if mid plus 1 and mid minus 1 are both not maximum, if either of these is maximum, just return that. Otherwise, if these are not maximum, you'll have to check this mid with the lowest value, that is the lowest in the current range. If the lowest value is more than, if let's say, if the lowest value, that is in this part, if we have something like this, that this is my low, this is my high, and if this value turns out to be more than, and this is my mid. So if this value turns out to be more than your mid, then you'll shift to your left range. Otherwise, you'll always shift to your right range. You will have something like this otherwise. Is it clear? This is low, this is mid. There is only this way, like there are other complicated ways, like I said, but this is the most easiest way. And believe me, if you are going with other ways, it will be much more harder and it will be much more difficult to prove your solution. But believe me, you cannot divide your range into two. Like if you want to see, first of all, if this problem is asked in an interview, they'll expect you to apply binary search only once. See, in CP, you can apply binary search as many times. You can apply it 10 times and your solution will still work. But the correct way of doing this is apply binary search only once. So I'll explain this once again. If it is like, if the, first of all, implementation doesn't matter at this point. If this approach, if the idea is not clear, I'll explain it again. Also, someone asked, is like rotation is happening in only one direction? Like it actually doesn't matter. See, if I have 1, 2, 3, 4, 5, if I rotated this once in left direction, I'll get 1, 2, 3, 4, and 5. If I rotate this thing same in right direction 5 times, you'll get the same thing. You rotate this thing 4 times. First one will come here, then here, then here, then here. So you'll have to rotate 1 to 4 times. So if you'll rotate this thing in right direction 4 times, it will be 1, 2, 3, 4, and 5. So it doesn't matter if the array is being rotated in left or right. It is just being rotated sometimes. So now I'll cover the complete explanation once again and pay attention, okay? So earlier we were discussing, now I'm telling you the solution and kindly follow this, okay? So we are given a rotated sorted array. So in this, let's say the function is going to look like, it can either be like this or it can be something like this, with the values, if I plot them. So now what will we check? We'll find the mid. Mid is nothing but low plus high by 2. So low initially is 0, that is the 0th index, first index, and high is n minus 1. Now I'll check if whether my mid is the maximum element itself. How to check this? If you want to check this, you can just check if the element next to mid plus 1, that is mid plus 1, if mid plus 1 is less than mid, then my mid is answer. We know this because the maximum element is only the element which is having the next element smaller than it. If this is not true, what will we do? We look at the graph again. See, okay, this is not possible. This, if our mid was this, we'll find that, okay, if our mid is this, okay, one more thing, actually the array sorted, I cannot do this more than this, I am making it wrong. It will be hard to visualize. If my array sorted, it will be something like this. Now let me draw a line. So your value will be up till at max this point only. You cannot, like this value cannot be more than this value, right? Because it was sorted and then it was rotated. So how can this value jump more than here? So now if our mid is this point, see, if our mid is this, we'll check if a of low, this point is low and this here is high. So if a of low turns out to be less than a of mid, then what will we do? We'll shift to the right part, right range. We shift to the right range. If otherwise, let's suppose our mid was here. You can look at this. Let's try to picture this. If our mid is here, now if a of low is more than our mid, a of mid, then we'll always shift to the left range. Left range. Is it clear now? Yes, no, anything? What about others? Okay. So now this is basically when we don't have a monotone, how to solve the problem then. So basically you first have to find a pattern for the thing that you're trying to find. You have to find, okay, A is low, is mid. It's not like, in this, we are assuming that the array elements are not, like array elements are unique. If the array elements are not unique, then it's only possible that the value of low and mid is equal. So then also you can make the same graph, right? You'll have something like this. Like some elements are same, then it's increasing, then it's same, then increasing, then same for a range, then increasing, then it drops, and then there is, okay, I'll draw it. So after this point it's same, then it's increasing, then it's going like this again, then it drops, so then it's like this, then it's like this. So you can again apply your same approach, right? For this point, it still holds the same thing true. So you can check if your mid is here, you'll have to just check one thing, that if your low is like currently, if your low is here, see, if your mid is at this direction, you'll change your low to here. But if your mid is in this direction, you will change your high to here. So this is nothing but you'll have to check extra conditions using if else. That if, how will you check this? You just have to check if your mid is equals to this thing and the next element is more, then you'll change your low to mid. That is, you'll shift to right range. Otherwise, you'll just have to check if the next element is now equals to this mid and the previous element was less than. So you were in increasing part and now low is also equals to this mid. So by default, you will change to left part. So this is just like the original problem statement remains same. The idea remains same. You just have to check some extra conditions. The idea is if the function is not monotone, what will you do? You'll have to check for some special special condition for the peak element. Like this thing should be, the thing that you're checking should be only valid for our particular position, for the position that we're trying to find. So check for some special condition that is only valid for our peak element. So in this case, or I won't say this is peak, but the result that we want, that is only valid for the result. So in this case, it turned out to be that the next element is result. So in this case, it turned out to be that the resulting position will always have the next element smaller. But this is not always true. Sometimes this will change. And then finally, how to decide the range, we'll have to look at this lowest element. And using that, you can shift, right? In either left or right range. Is it clear? Okay. So I'll quickly show you the code. So this is the implementation. In this, we are having a low to high. Initially, low will be 0, high will be n-1. Then we find the mid, and then we check if the mid reaches 0. That means that we have reached the starting, like this low position. So if the, and we'll also check that if this mid is more than this element. So if this mid is more than this element, then by default, this is our peak, right? So we can return this right away. Otherwise, we'll check if mid or either mid plus 1 is peak. If mid plus 1 is peak, then this mid plus 1, where is it? This mid plus 1, if ARR mid is more than this, and this mid is more than 0. So this is also like, okay, this is also checking that only the mid is maximum. So this is in case when mid is between high, low and high. And this is in case when it has reached one of the corners. So in that case, when it has reached one part of the boundary, then we cannot check before it, right? We cannot check for mid -1. But here, since it is in between, we can check for mid -1 also. Otherwise, like I said, if ARR of low is more than mid, we'll shift to the right. This is left part, and otherwise we'll shift to the right part. Is it okay? Is it okay? We can write iterative, like there is no, you just call the, you just put a while function here while low is less than high. So now let's go to some ternary search. Like we'll discuss ternary search now. Okay, like let me see what else was. So we had to do, this is done, this is done. Okay, let's first look at square root, then we'll go to ABS and TS. So, okay, till this point, what do you feel about, like, am I going too fast or too slow? Okay, so now one of the things in advanced binary searches, when you're working with decimals, that is floating point numbers. So in advanced binary search, when we're working with decimals, we have something kind of error, because see, if each time if we keep decreasing a range by a factor of 2 for integers, it makes sense, right? Because initially our range was maybe 8, then it will become 4, then it will become 2, and finally it will become 1, and then 0, right? So we are reaching this point, but this is only valid for integers. If we look at decimals, if let's say our range was initially 8, it will become 4, then it will become 2, then it will become 1, then it will become 0.5, then it will become 0.25, then we'll decrease our range further by 2, by a factor of 2, it will become 0.125, then it will become, like, you get my point, right? So this is never ending. So you should have a value, that is, you won't be going after this point. So this is basically that error. That, see, if your range is this thing low to high, you know surely that your answer, what is low to high? Low to high is nothing but it is the range in which your answer lies, right? yes, no, initially it is everything, then we keep discarding either of the half parts which cannot be our the part in which our answer cannot be in, right? What is binary? See, in by initially we have the complete range, then we either discard this part or this part. On what basis? If the result cannot be in this part, we'll discard it, right? So low to high is nothing but it is the range in which our answer can be. So finally, once our low to high is less than some, let's say 10 to the power 6, this means that our answer is in this range only, and this range itself is less than 10 to the power minus 6. So if I output this thing, then the error will be less than, even if the answer is high and I printed low, my error is less than 10 to the power minus 6. So do you get my point? What is the meaning of error here? Why do we need error? So now let's look at one of the problems that is very common. See, if you want a square root of a number, how will you find the square root of a number using binary search? See, you get an inbuilt function in C++, which is sqrt, but there is a precision error in this. If you look at that, like the precision is not that great. Sometimes for a big number, the precision is around 2 or 3. So this is huge. Usually you want precision around 10 to the power minus 6. Okay. And by the way, the complexity of this thing and this thing is nearly same only. If you do using, like, if you'll implement your own square root function, and like usually if you look at some people's code, if you see some high-rated people's code, you'll find that they in their template they have mentioned like they always keep a square root function, and they use their function only because the chances of having unexpected values as output is very low if you have implemented your own function. Then why there is also one other reason why not to use inbuilt function, because see, sqrt only works up till 10 to the power 9 if the value is up till 10 to the power 9. If you have values more than 10 to the power 9, such as 10 to the power 18, you will have to use sqrtl, and sqrtl will give you more error. The precision of this thing is like far less than this. So now let's look at how to like write our own square root function. So first of all, see, we have to find square root of n, and n can be decimal as well. So how to find this? Anyone? See, what will we do? We'll take our low as 1. We'll take our high as maybe close, like something like we can take any value. Let's take n only. So while our low is less than or equals to high, okay, we cannot do this thing. Why? Because these are decimals now. These are decimals. So what will we do? While our high minus low is more than or equals to 10 to the power minus 6. Because this will keep on going while a range of like the possibility of a result is more than 10 to the power minus 6. So while this is true, what will we do? We'll find the mid. We'll find the mid here. And we'll check if mid into mid turns out to be less than or equals to n. We'll take our answer as mid and we'll shift to the right part, which is low is equals to mid plus 1. Not mid plus 1. What will we do? Can anyone give me any idea? What should I write here? Like usually I write mid plus 1, mid minus 1.
Mid plus error.
Yes, I will write mid plus 10 to the power minus 6. And similarly in else part, I'll write high is equals to mid minus error, that is 10 to the power minus 6. So this is the template for advanced binary search. Like when you're working with decimals, this is what you will follow.
How much will be the precision if we keep 10 to the minus 6?
The precision will be 10 to the power minus 6. The maximum error that you'll get will be 10 to the power minus 6 only. Why? The worst case scenario is what? You'll answer low and the answer was high. Because see, what is low to high? Low to high is nothing but the range in which your answer will lie in. So your answer can be anywhere between these two. In classical binary search, at the end, low is equals to high. So there is only one value, but here there is a range left. But since you're answering low, maybe your answer was high. But what is the difference between these two? It's 10 to the power minus 6. So your maximum error can be 10 to the power minus 6. Is it okay?
Okay.
Now, these are the changes that are like the advanced binary search. When you're working with decimals, these are the changes. This thing is different. This thing is different. This thing is different.
Why are you adding mid plus 10 to a minus 6 to low, like low equal to mid plus 10 to a minus?
See. If here I've already said that my answer is mid, right? So there is no point in checking. See, my answer is mid, this thing, and I'm giving my low something which is mid plus 10 to the power minus 6. So there is no point in checking in this range anymore, because if the answer was actually in this range, then this will also work, because the precision, like the error which is allowed is 10 to the power minus 6. So check for that range, which is like which will affect actually, which will have some value, because there is no point in shifting this mid from here to just this somewhere in between. Because if this is the actual answer, then this will also work. Is it okay? Because this much error is allowed.
Why mid plus 1 will not work like on
See, mid plus 1 will simply mean, okay, mid, you had mid like here, this is the complete range. mid plus 10 to the power minus 6 is somewhere here. So, but mid plus 1, if you do low, if you do something like this, you're completely ignoring this part. Maybe your correct answer was somewhere here. So this is more than 10 to the power minus 6 now, right? So the error will be much more.
Okay.
Okay, I'll give you an example. Suppose mid is 1. You had to give low as 1 plus 10 to the power minus 6, and the actual answer is 1.5. 1.5 is square root of which? 1.5 into 1.5 is 2.25, right? So initially you were given the number as 2.25. You checked for mid. Mid is 1. So 1 into 1 is less than 2.25. Yes, it is. So your answer will be now equals to 1. But if you directly blindly give low as mid plus 1, that is low is equals to 2. If you change your low to this thing, now there is no answer in low to high range. Why? Low itself, 2 into 2 is itself more than 2.25. But your answer was 1.5. Now your error is 0.5, which is much more than 10 to the power minus 6. So now we have looked at what is advanced binary search and how we work with decimals, right? So let me find one problem and okay, first let me show you the implementation of this. Okay, where is it? Okay, let me, I think I'll have to copy it. Okay. Okay, I don't have it with me right now, but you get the idea, right? If someone wants, I can write it quickly. Okay, let's skip this. We'll go ahead and we'll cover.
Hello.
Yes.
Yesterday you told that once we have to iterate from the range log base 2 into to the power error into high. What is that case?
Yes. I'll cover that also today. So
Okay.
let's discuss that thing only first. So maybe you are given that the final error that is allowed is maybe 10 to the power minus 9. So instead of always working with errors like low plus, see 10 to the power minus 9 is a very small number, right? So if you are working with something like if you're doing low is equals to mid plus 10 to the power minus 9, the compiler will simply ignore this thing. Or if you'll do high minus low is equals to, while this is more than 10 to the power minus 9, this will sometimes not actually work the way you want it to. Why? Because this value is very low. The compiler will make make 0 out of this. So like if you'll check in your functions also, if you will find like 1.000000, if you maybe have this kind of, if you have many zeros, the precision after some digits is not that great, right? So in those cases, what we tend to do, if you want that much precision, maybe instead of having while low high minus low more than equals to some error, but see, we know that this error is in 10 to the power 9, right? So basically 10 to the power 9 error is in order of 10 to the power minus 9. So if let's say our original range was 10 to the power 9 and we want to make our range go from 10 to the power 9, initially the complete range, the length of this complete range was 10 to the power 9, and we want to make our range 10 to the power minus 9. So what is the factor by which my range got decreased? What is the factor?
10 to the power 18.
Okay, so 10 to the power 18. Now, how many times? See, if I want to make this 10 to the power 9 go to 10 to the power minus 9, how many times should I divide it by 2? 64 times, right? Yes, no, anything? 2 to the power 64 is nearly equal to this number. I think it was 2 to the power 63 or 62. So now, instead of writing it like this, can I not just make a loop for which will iterate 64 times, and here I will do everything else. Like I'll do the same thing, mid, low, high, like my complete implementation. So this will guarantee that my range, like low to high, now after 64 iterations is like the range is now in order of like the length of this range is 10 to the power minus 9, right? Yes, no, anything?
What can be the range of the error in the question?
Like if in this problem, the range of error is 10 to the power minus 9, if you have to be really precise, right?
Okay.
So you're getting my point, right? Instead of writing it as, okay, let's write, okay, I'll write both of those square root functions, like trying to find the square root using while loop, or maybe when the error is, when the error I want is 10 to the power minus 6, and using some for loop when the error is maybe again 10 to the power minus 6. So let's say n is up till 10 to the power 6. So I want my low will be 1, my high will be, I'll quickly write this, okay, high will be 10 to the power 6. Then while my low is less, okay, I cannot write, while my high minus low is more than or equals to 10 to the power minus 6, what will I do? I'll do mid is equals to low plus high by 2. Now, if mid into mid is less than or equals to n, I'll say that my answer is at least mid, and I'll say low is now equals to mid plus 10 to the power minus 6. Otherwise, else I'll say my high is now mid minus 10 to the power minus 6. Finally, I can return my answer. This is the square root of this n, which I had in input. Okay, is this thing clear to everyone?
So here we are not iterating that for loop.
No, I'll do that here. This is okay, right? Now doing the same thing using for, if I for int I is equals to 0, now from 10 to the power 6, I have to go to 10 to the power minus 6. So this is 12, 10 to the power 12. So this is nearly equals to 40 iterations. So I'll say I is less than equals to 40, I plus plus. So now I'll do the same thing, like whatever you have done here, copy the same thing here. Mid, find mid is nothing but low plus high by 2, and check the same if condition here, update your answer and low here, then write else and high here, and finally you can return your answer here. So this also guarantees that your answer is of precision at least 10 to the power minus 6. But this doesn't depend on some decimal value, some floating point value. Do you get my point now? Yes, no, anything?
How
So
are you
Bhaiya,
calculating this number 40? Like, how are you coming to the conclusion that iterations will be 40?
Okay, how am I coming to that? See, from 10 to the power 6, I had to go to 10 to the power minus 6. So what is the range that I have initially? I have a range to,
Then
like
you are
the factor that I have to decrease this by is 10 to the power 12. 10 to the power 6 divided by 10 to the power 12 is 10 to the power minus 6, right? So this is the factor that I have to decrease my range by. So what is 2 to the power x? Like what is the number of iteration that I need? Because each time my range will get decreased by half. So what is this x for me to get 10 to the power 12? So if you will take log, so x log 2 is 12. So x is nothing but log base to 12. No, I think this is 12. This is log 2 10 to the power 12. So this is 12 into log base to 10. So this will be nearly equals to 40, less than 40. So I'm taking an upper bound. Is it okay? Is it clear?
yes.
This is clear to everyone, right?
Bhaiya, the for loop approach would be helpful in the
Like this is
10
much
to 10 to power
better if you are working with some precisions. Like you'll find this thing in many of the high rated programmers. Like they don't write binary search as this. Sometimes when you are working with decimals, why? And now like you probably think that this is not binary search. I'm not able to see this template, right? But this is actually a better way to write binary search when you're working with decimals, because this will guarantee that your final result is in, or like the precision is at least this much. So I won't be wasting any much more time in this. Let's go ahead. So now going ahead, we have covered these things. So let's look at what are the things that are left. Okay, we have to discuss this thing. This is done. This thing is done. We have covered till, like, okay, cube root is same as this thing. Instead of checking if mid into mid is less than equals to n, you can check, like here we were checking if mid into mid is less than or equals to n. In case of cube root, you can make your own cube root function also if mid into mid is less than equals to n. Just this thing is the difference. Okay, so these things are done. Now coming to some problems. Okay, we'll solve problems. Enough of theory. So let's cover one problem and then we'll look at some ternary search also. But let me know everything is clear till this point, right? Yes, no, anything. See, these are some things that you won't have done earlier. So yeah, like these are new. You'll have to solve some problems. Then these things will stick to you. But these are very important things. Okay, and what about like, is someone still feeling that I'm going slow? Okay, so the problem that we're going to do is, okay, let's not do interactive first. Research.
Hello.
Yes, yes, yes.
We did not receive the yesterday's interactive code you have written. It
I
would be
shared
helpful if you share.
it in the chat. Like maybe someone has it. I shared the complete code in the chat. I'll share it again after today's class. Okay, just remind me. So let me see. Okay, there is no point in doing binary search problem because we have already done those. Let's pick up one interactive plus binary search, and then we'll go to ternary search. What do you say? We have discussed interactive problems yesterday. I won't be going through the theory. So let's pick up this problem. We'll just quickly do this problem because then we have to go to ternary search plus this ternary search plus interactive. So basically, this is an interactive problem. In this problem, we are given that Polycarp is playing a computer game, and in this game, an array consisting of zeros and ones is hidden. Then Polycarp wins if he guesses the position of the kth zero from the left t times. Now, Polycarp can make no more than 20 requests of the following type. So he'll ask question mark LR, which is for the range LR, find out the sum of elements in position from L to R. So since this is an easy problem, we are given t is like t is always equals to 1. So, and to make the game more interesting, each guessed zero turns into one, and the game continues on the changed array. So basically, see, initially what we had an array consisting of zeros and ones. Now we like Polycarp had to guess the position of the kth zero from the left, and we in this easy problem we have to do it only once. So forget about this t, like this t is existing. You just have to find the position of the kth zero from the left. Kth zero is basically, I'll show you. I'll write it once. So now if we have this thing, and there is one more thing, that after each guessed zero turns out into one, and game continues in the changed array. And more formally, if the position of the kth zero was x, then after Polycarp guesses this position, the xth element of the array will be replaced by 0 to 1. So this thing actually doesn't make, like, this complete thing isn't making sense if you have t is equals to 1, right? Because you have to guess only once. So the problem statement is clear that if we have L to R, like for a range, we'll get the sum of the elements, and we have to guess the first, what is the place of the kth zero. So kth zero is nothing but, if I write the problem as, if I have elements like this, and I have to find, let's say, the third zero, so this is the third zero. And from L to R, if I write it as, if I ask the compiler, okay, give me the range, the sum of L to R, the compiler, if I have L as this and R as this, it will give me the sum of this range. So this is 2. So you get the point, right? You get the problem statement. So now tell me, now let's discuss how to solve this problem. Anyone? Also, we can only make 20 requests, and n is, okay, these are also two things. N is less than or equals to 2 into 10 to the power 5, and queries, like the number of queries that we can ask is 20 at max. So how to solve this problem?
Like the number of zeros would be total range minus the sum in that range.
Okay. See, if you calculate, if this is the array, and you calculate prefix sum, for this, like from starting from here, and you'll see that the prefix sum up till this point, if you find the prefix sum of this range such that the sum is equals to, let's say, okay, sum, if you find n minus sum, so this is basically the number of zeros that you have in this part, right? N, okay, and let's not write it as n, I'll write it as L, and this is sum is from 0 to L. So L minus sum of 0 to L is the number of zeros that I have in this range. That is in range 0 to L, right? Yes, no, anything?
Yes.
Okay, so can I not just simply apply binary search on my prefix sum? Right? We can do this. And one more thing. First of all, everybody knows that this is a monotone, right? I don't have to prove it. Okay, I'm not going to prove if this is a monotone, because it is, like, it's very easy to see that. It's an easy observation. I'll prove one thing, that in 20 queries, we can always find the answer. See, if the range is 2 into 10 to the power 5, finally, this is an initial range length, and finally, we want to reach our range of length 1. So how many times we are decreasing our factor by 2 into 10 to the power 5? So let's say we are doing it 2 to the power x times. Like each time, if we did x operations, we'll have the range to decrease these many times. If you again take log, x is nothing but log base 2 into 10 to the power 5. So can someone tell me what is this value? This is nearly equals to 17, I think, 17 or 18. Can someone verify this? It will be 17 point something. Okay, so basically you can find the answer, you can decrease your range of this size to this size in these operations. So that's why in 20 queries, you can always answer this. So I'll show you the implementation once quickly, because there's no point in wasting time on this. Give me a minute time. And one more thing is, like, okay, first of all, the rating of this problem is 1600. You guys didn't have to think much, right? If you know about interactive problems, if you know how interactive problems work, you can easily solve this using simple binary search, right? You don't have to think much. So basically, problems which are interactive are like, their rating is much more than their counterpart problems. So I think the second problem, which is the second part of this, if like there are more than one queries, like each time if you have to answer the kth, what is the position of the kth zero, and the last, like if the last time the zero was here, like the kth zero was here, this will now become 1. The rating of this problem will be around 1900 or 2000. So I'll give this problem as a daily task. It is also easy to solve. You'll just have to make some extra computations after each processing. Okay, so let me copy my implementation once. Okay. So is the what are you guys seeing right now? Are you able to see the code, or you okay? Okay, I don't know why this is frozen. Give me a second again. I'll start my screen share again. Okay, you're able to see the code now, right?
Yes.
Okay, so this is the implementation. In this, I haven't written that ask function because I solved this very long back. But it's always recommended to have your have your ask function different. But here, what I'm doing, see, initially my range is this. While my range is more than 1, I'm asking the sum of this range. Then this is actually, I haven't actually calculated mid also. This is mid. Now, if the number of zeros, like I said, if the number of zeros that I want, this is the number of zeros, right? So if my number of zeros is more than this value, then I'll decrease these from my the number of zeros that I want, and I'll shift to the right part. Why? See, this is also important. If I'm shifting to the right part, if let's say this is my original and this I have something like this, and I have to find the, let's say, fourth zero. So what is my mid? My mid is maybe, let's say, this. So how many zeros I have till this point? I have 2 zeros. 2 is less than 4. So you cannot blindly shift it to the right range and say that I'm still looking for the fourth zero. Why? Because you have already found 2 zeros. So now you are only looking for the second zero in this range. If this is a new range for you, you're looking for the second zero. So now this is your second zero, right? So this is what's being done in this part. If you're shifting to the right range, make sure that you're decreasing your position. Otherwise, no need to decrease your position, and you'll shift to the left range. Finally, you can answer it as well. So, okay, this is clear. So we have done an interactive problem. Now I'll discuss ternary search. So is anyone having any doubt till this point?
Can you tell us the last part again, like this second to fourth?
See, if in this problem, if you had to find the fourth zero, so first you maybe, let's say this is your mid, right? So how many zeros are in this range? 2, right? So
if we calculate sum from 0 only, then what will happen?
Yeah, you can do like that also. If you'll implement always, you're starting from this part only, then you can do that. Then you don't have to decrease it. So then you'll always, your low will never change. You will accordingly shift your mid. You can do that way also. Like I'll give you this problem as your like one of the DRs, and you try to solve it. Like I'll not give you this problem. I'll give you the harder version if it's okay. You guys, like you're finding the interactive problems are not that hard, and plus you'll get the confidence of solving these problems. So I think the harder version was around, let me see what was the rating. Okay, it's 2200, so I don't think it's a good option to give it. But I'll look and find another problems. But I think those problems are also easy only. But I won't give a 2200 problem in level 3. So, but yeah, I'll suggest that if you want, you can solve, like I'll give you the link of this problem. You can solve the harder part of this problem. That I can give you the problem in the chat. And I'll give you the harder version also. So if you want, you can go ahead and solve this. The idea will remain same. You'll have to just do some extra computations. So I've given both the problem links in the chat. Try to solve this problem on your own. I won't be giving these problems in your DR now. So let's go back to discussion. So now we'll discuss some ternary search. So first of all, let me know everything is clear till this point, right? Okay, instead of writing yeses, let me know if anyone is having any doubt till this point. Or like is some of you people feeling that I'm going fast or maybe I'm going slow?
Yes, sir.
Yes,
Hello?
yes.
Can you repeat the previous position wala part? I didn't get it to how do you calculate the position
I have solved it. I'm moving my low
in the
part.
code, in the implementation.
Okay, maybe those variables, like you're getting confused because of this variable name. This position is nothing but you have to find the position of the kth, like this 0, and this value is always 1. This, so this doesn't actually, like the nomenclature is not that correct, but other than that, you have to find the k, this 0, this, let's say this is except 0. So if this except 0 is more than the number of zeros available to me in the left part, I'll decrease those zeros from my left part, and I'm going to shift to my right part. Is it okay?
Okay.
So Now let's come to ternary search. So what is ternary search? See, we have looked at binary search, we have looked at interactive problems, but ternary search is different. Why? Because in this, we have a function like this. So yesterday I explained some parts to you, but not completely. So today we are going to look at this. And we have to usually find the point of minima or point of maxima. So initially our low is in this, let's say our low is this, our high is this, and okay, like we'll divide this range into three parts. So this is first part, this is second part, this is the third part. So this is your mid one, and this is your mid two. So what we do in these problems is usually we check if the mid one turns out to be, see if, okay, first I'll stick to one case. Let's try to find maximum only. So I have my low here, my high here, maybe my mid one here, and my mid two here. So mid one, mid two, high, and low. So what we do, if my value at mid one turns out to be more than the value at mid two, then my high will change to this, because the maxima is always in this part then. So my high will become mid two. Otherwise, if this is not the case, else my low will become mid one. So let me show you that case also. In this case, when I have something like this. So this is my high, this is my low, this is my mid one, and this is my mid two. So in this case, since value at mid one is less than value at mid two, my low will come to mid one because the maxima is in this part now. So is this thing clear? Like how ternary search works? What about others?
So there is only these three possible cases.
Yes. Like not three, two cases.
Okay.
Okay, like majority of people are not responding in the chat. If you want me to repeat once, write it down. If it's clear, write it down. Okay, so I'll take the other case now. Like I'll repeat it, but I'll repeat it using this minimum one. Is it okay? I had taken this case, right? I'll show the working with this one. So let's assume that this is the function that we have and we want to find the minima. So this is our low, this is our high. This is our low, this is our high. And we have to find the point of minima. So maybe this is our mid one, this is our mid two, M1 and M2. I'll give you in a minute, I'll just tell you what these M1 and M2, how to find these M1 and M2. Like in binary search, we find the mid as low plus high by 2. So yesterday also I discussed this, but today also we'll go through that. So this M1, if in this case the value at A of M1 turns out to be more than the value at M2, then our low will come to mid one, M1. If this is true. Otherwise, our high will come to low 2, M2. If the value at M2 was more. So we all see, if we have to find the minima, we'll always shift our boundary to that position which is having more value. Shift boundary, shift that boundary which is closer to more value. Okay, to more value. And if we have to find the maximum, then shift boundary to a lower value, to lower value of M1 and M2. Okay, lower value. So see, in this case, if we are finding the minimum, we have to shift our boundary to the value which is more. In this case, if M1 was having more value, we'll shift our boundary to M1. Otherwise, if M2 was having more value, then we'll shift our boundary to M2. In this case, when we are finding the maximum, we'll shift our boundary to minimum. So like the minimum of M1 and M2, it's always opposite. Remember it like this. So if our value at mid 2 is low, then we'll shift to mid 2. Otherwise, we'll shift to mid 1. Opposite in this thing. See, if our value at M1 is low, then we are shifting to M1, right? So remember it like this. If we are finding the maximum, our boundary will get shifted to minimum of M1 and M2. If we are finding the maximum, then our boundary gets shifted to lower of minimum and M1 and M2. Is it clear? Is it clear now? Okay. So now, how to get these M1 and M2? See, there are many ways to get this M1 and M2, but the most optimal way to choose M1 and M2 is such that, see, you divide all of these ranges. See, the probability of finding the answer in any of these three ranges is equally possible, right? So try to make these ranges of equal size. So what is, you have to divide this complete range L to R in a range, in three ranges of equal size. So the range of everything should be, the size of everything should be, if the initial was L, then these three should be L by 3 size, right? Yes, no, anything? Okay, like graph is testing. If it is a parabola, it will always work. It will work like this only. If it is a parabola of any kind. Like if it is, sometimes you'll find these, like these are more advanced problems. I don't want to get into these. Sometimes you will have a parabola of like this also. Like you'll have to maximize, so you'll have to change your axis only in that case. Okay, so like you can simply view, instead of watching it like this, you can tilt your axis and you can view like this and find the point of this minima. So this is just like, those are just implementation level details, so let's not get into that. So basically, if we want to divide our range into all by L by 3, what should this be? What should be M1 and what should be M2? See, M1 should be L plus 1 by third of this complete range. The complete range is R minus L by 3. And M2 should be R minus L by 3. 1/3 of this. So I just wrote these yesterday also, but is this thing clear why how these values are coming? And by the way, yesterday also, if you look at the slides, I always, like along with my slides, I also share the notes that I have written. I've shared those yesterday also, and I'll share them today also. Because if you miss something during the class that you're not able to write, you can like refer the notes later on. So, okay, this thing is clear. So now let's look at a problem. It's like the ternary search is clear to everyone, right? Okay. Sure, what is happening? Give me a minute. Okay, it's yeah. So let's look at one of the problems, which is yes. Yes.
It is possible that the value at mid1 and mid2 can be equal also.
Yes, it's possible. So that's why I have written equals here, right? It's equal. Then you can pick any of the cases. Like try to draw it once. Okay, I'll draw it quickly. See, if the value at M1 and M2 is equal, if your value at M1 and M2 is equal, by the way, like let's say this thing, then you can either shift to this range or you can shift to this range. The mid is somewhere here. Also in the case of minima also. So it doesn't actually matters which you are picking if these both are same. Is it okay? Like in that case, if you want to be like, you want to enhance your like the performance of your algorithm, you can actually, instead of shifting one of your boundaries, you can shift both of your boundaries to these. But in an average case, this won't make any difference. Like the time complexity will still be the same. But yes, in that case, if both values are same, you can change your low and high to both of, like you can shift both of your boundaries. So in a way, your algorithm, like since earlier a range, like only 1/3 of your range was getting like ignored, now you're discarding 2/3 of your range. So it's a bigger chunk that you're now discarding. So now your range will get shorter faster. So you can do that in this also in that case. But there's no point, like it doesn't have any that practical impact on your runtime. Okay, I'll move to the, now we'll move to one of the problems. Let me clear my screen. Okay, let's do. Okay, let's do. Let's do this problem. This is a ternary search problem. See, now don't look at the ratings of the problem, because see, let me tell you, if you look at, see, ternary search is itself a very advanced topic. So ternary search plus, if you look at problems with ternary search plus interactive or interactive plus advanced binary search, the problem rating will be high only. But you know all the things, like I've covered each and everything that is required to solve those problems. So there is, see, you won't find ternary search problems of rating 1400. The rating will be high only. So we'll solve this problem, and like the problem rating is 2000. So, but it actually doesn't matter because the problem is quite easy only. So let's look at this problem. In this problem, we are given a sequence of n integers a1 to an, and we have to determine a real number x such that the weakness of the sequence, that is a1 x, a1 minus x, a2 minus x, each element we are decreasing x. So we have to determine a real number x such that the weakness of this sequence is as small as possible. Now the weakness of the sequence is defined as the maximum value of the poorness of all the segments. So maximum value of poorness over all the segments. So what is this poorness? The poorness is nothing but poorness of a segment is absolute value of sum of elements in a segment. So let me like first write this everything, like the information. I'll write this here. So we are given an array A all the way till AN. So in this array, we have to determine a real number x such that the weakness of the sequence. So we have to determine real number x such that the weakness of the sequence, which is A1 minus x. Such that the weakness of this thing is minimized. We have to bring it as small as possible, right? So the weakness of this sequence should be minimum. Now, what is weakness? Weakness is defined as the maximum value of the poorness over all the segments. So this is itself the maximum value of poorness. What poorness is? Poorness is nothing but the poorness of a segment is the absolute value of the sum of segment of the elements of the segment. The poorness. So we have to maximum value of poorness. This poorness is nothing but the absolute sum of segment. Absolute value of the sum of the elements of the segment, sum of the sum. So now we have to find what is the value of x such that the minimum weakness, such that we get minimum weakness, and minimum weakness is nothing but we want the minimum maximum value. Let me write it in a statement. Minimum maximum value of absolute value of the sum of segment. So this is what we want, right? We want to minimize the maximum value that is of any segment, like the absolute sum of any segment. Is it clear? Okay, we have a segment.
Can you list it through one test case?
Yes. I'll take a test case also. So let's pick up one test case. Let's pick up 1, 2, 3, 4. Okay, 1, 2, 3, and 4. In this test case, if x is 2.5, then the elements will become 1 minus 2.5. That is minus 1.25, 1.5, minus 0.5, 0.5, and 1.5, right? Then the maximum poorness occurs in the segment. What is maximum poorness? Maximum poorness is nothing but the maximum sum of like a maximum absolute value of sum of a segment, value of sum. So if you look at the sum of this, it is minus 2.5. The sum of this is also 2.5. So absolute value here is also 2.5, and here it is also 2.5. So this is the maximum absolute value of sum. So this is the poorness. What we had to do, we have to minimize the weakness.
Some value, how some value is 2.5? It should be 2, no?
Yes, it's 2. So this is like here also the absolute value is 2, and here also it is 2. So now we have to just we can see that if we choose any value of x, this is the least value of weakness that we can get. So like instead of looking at weakness and this, we just have to minimize the maximum value of any segment's absolute sum. Like if you are given an array, what you have to minimize the following thing. You pick up like among all the segments, the sum of this thing, you have to minimize this thing, absolute sum. Is it clear?
What in that test case if we take the whole array, and what would be the sum of that?
If you pick up this complete, right? So
yeah,
if you like, that is also one of the this is also, but since poorness is defined as the maximum sum of any segment, so there are n into n segments here. Out of those n into n segments, you have to pick that segment which is giving you maximum sum, and eventually you have to minimize this maximum sum. See, you are given some elements. You have to decrease x from each of these. Finally, you'll get a new array, and in that array there are n square total subarrays, right? There are n square total subarrays. Out of these n square subarrays, you will pick the subarray which has the maximum sum always. So for this x, for each x, you will get a maximum sum, right? And you'll have to choose x such that this thing is minimized. Is it clear now? Like in this case, you can choose this segment is also there, which is having 0 as, which is having 0. If you take the complete segment, the sum is 0. But you have to pick the segment which is having maximum absolute sum. So this is the segment, and also this is the segment which is having maximum absolute sum. Is it clear now?
Yes.
Is it clear to everyone? Okay, so now tell me how would you approach this problem? Any idea, like any, if you don't have to be completely right, you just have to give me like any intuition that you have.
Answers.
And one more thing, if you, okay, let me show. This is also that advanced binary search problem that we discussed, right? That we are working with the decimal. See, in this problem, you have to answer x is not an integer, but a real value, real number x. And one more thing, in this, we are given that the absolute error should be less than 10 to the power minus 6. So anyways, yes, you were saying something. This is a hard problem, don't get demotivated. But this is covering every topic that we have covered till now. Okay, I haven't really said that I'm going to apply ternary search on it, but anyway, it's like I'm asking you, how would you have, like, do you have any intuition how to solve this problem? Okay, instead of writing in the chat, just like you can unmute yourself and you can say it out loud.
We will divide the interval into n parts.
Yeah, like I'll discuss it. See, first of all, let's see if you are solving any binary search problem or ternary search problem. See, in binary search, you can just start writing the code, but in ternary, okay, I'll share the problem link first. Okay, my screen is frozen. Like, let's first discuss, then I'll share the implement. Then I'll share the link. Okay, I'm not able to go to that screen right now. This is visible to you, right? Okay. Okay, what is happening? I'm not able to erase this thing also. Okay, it's clear. So now, in cases of ternary search, it's always better to write mathematical equations. Why? You'll need mathematical equations to prove, like, you'll know on which thing you need to apply ternary search, because ternary search is not that obvious. Believe me, you'll have something like ternary search is usually involved in those cases in which the equation itself is of second order. So it's not that obvious to apply ternary search. Like in this problem, you have no idea how to apply ternary search. But let's look at the problem one. See, in problem we are given that sum of ij, like sum of ij, let's write this as sum from I to j. This is sum of I to j, and this is nothing but sum of, let's say you have decided that there's some x. So okay, my computer is lagging a bit, but bear with me. So for every value from I to j, this is the sum, this is giving me sum of I to j. Now, what is the thing that I have to find? I have to find the maximum value of, okay, for like my I will go from 0 to n, j will go from I to n, and maximum value of sum ij, absolute value. Is this thing clear? Yes, no, anything? And finally, what I have to do, I have to like pick a x such that this value is minimized. Is anyone having any doubt in this part till now? This is my sum. This is the sum of all the segments. I have to take, okay, this is not maximum. I have to, like, where will I write maximum? Okay, yeah, like here I will write maximum. Out of all of these values, I pick up the maximum value of sum. Right? Now, instead of, see, what is A? It is minus A if A was negative, otherwise it's positive A only, right? So instead of writing this as this thing, I can write it like I is equals to 0 to n, maximum of all of these. J is from I to n, and maximum of sum of I to j, comma, minus sum, like whatever is bigger of these two, right? Yes, no, anything? Is the, like, is everyone able to follow till this point? If no, unmute yourself and ask me the doubt that you have to know. Okay.
So we have subtracted x from each index, right?
Yes, x is selected first. Basically, you have to find the x only. We have to find x only such that the value of this thing is minimum as possible.
Okay.
Okay. So it's clear, right? Now, okay, let's see this thing. Let's see this thing. So sum of I to j and minus sum of I to j. So sum of I to j is nothing but a of I plus a of I plus 1, everything till a till j. This is this thing minus j minus I times j minus I plus 1 times x, because everything will get subtracted by x once, right? Yes, no, anything. Like this is a really easy problem to like try to follow the maths. Okay, my screen is lying. I'm not sure why isn't this erasing. Okay, so this thing is clear to everyone. This is sum of ij.
Yes.
Okay, now let's write minus sum of ij. Minus sum of ij is nothing but j minus like the opposite of this, x minus this everything, a of I plus a of I minus 1, a of I minus 1, a of I plus 1, not minus 1, up till a of j. So this is minus sum of ij, sum of I to j, and this is positive sum of I to j, right? So now this thing is a constant, is it not? Like it is same of both of these, right? So
Yes.
let's draw the graph for this thing, sum of I to j, and for a fixed ij, this is x, this is x, this is sum of I to j. So isn't this that graph? This thing, if I draw this thing, constant minus some factor into x, will I not get this equation? Will I not get this thing? Yes, no, anything? If I keep increasing my x, will this value not keep on getting decreased? Okay, so now let's draw the second one also in the same graph. So what about this thing? This will be like this. As x increases, my value will also increase, right? This thing. So since I'm taking max of these two, maximum of these two values, so the final graph will look like something like this, right? These values will be like the minimum values will be ignored, right? So if we look at the graph, the thing what we are doing, this function is basically this thing. We are trying to pick these values for every I to j, and we'll always take the maximum of these two. Maximum of these two basically means for this point, for this value of x, you will take this value. For this value of x, you'll take this value. And if we see that this sum of ij, since we have to minimize the final value, we have to minimize this complete thing, right? We have to minimize this thing. So if we want to minimize this thing, we can, this is that x. Do you get it? This is the point which
Yes.
has the
Yes.
minimum value of x. So now this is a ternary search problem. Why? Because this is not a monotonic function. It is a U kind of function. Is it clear now? We can apply our low, high, and then we can apply binary ternary search on this. So are you able to connect how ternary search is applicable on this? We have to write the equations first, then we have to make the graph of two, then we have to merge the graph of two, and then we'll get this thing. So is this thing clear to everyone? Like this is advanced. See, this is a 2000 rated problem, but the crux of this is if you're able to draw, like if you're able to come to this point from this information, the information that is given to you in the problem statement, the problem is half solved. So now the only thing we have to do, we can apply ternary search. We'll find mid one and mid two, and now see at mid one we have to, at this mid one and mid two, we have to find the values. How to find the values? Mid one and mid two is nothing but the value of x, right? So it's nothing but you'll just traverse through your complete array, you'll pick the maximum values and you'll return it. And again, like I said, how do we solve this problem using ternary search? If we have something like this, low is here, high is here, this is our mid one, this is our mid two. So if low is, if the function value, if this is the value, if value at m1 turns out to be less than value at m2, where should I shift? Quickly tell me, where should I shift? See, in case when I have to find minimum, I'll shift to that place which is having more value. So I'll change my high to m2, and otherwise I'll change my low to, else low is equals to m1. Is it clear? Is it clear? Yes, no, anything?
Yes. Yes.
So can I show you the code? Like other than this, there is nothing else to discuss in this. If anyone else is having any doubt, you can ask me. Otherwise, I'll show you.
Like we are defining the convex type of function, the parabola, on every subarray. So
Yes.
I understand if I apply the ternary sites on every subarea. I'm sure to get the answer.
Not every subarray. Like sum of ij, basically this is the graph that you get out of this equation. Right? The first function is decreasing and the second function is increasing. If you merge those, you'll get a V-shaped function. So in that V-shaped function, you have to find the minimum. That is the intersection of the two functions. So in order to find that, and this is a real, like this value can be something like 1.2356. So that's why you have to, the answer is real.
It is for a subarray, right? How can we extend it for the whole array?
It doesn't, like I said, this value is okay. Like for every subarray, you're also seeing white. Okay, no, it's visible. So for every subarray, this thing is constant. This thing is not changing. For like if I to j is something, it is same here and here. The only thing that these two depend is on x. So for every subarray, it doesn't actually matter because these things don't actually change. These things are both same for both. Right?
Right.
So now eventually you have to find, see, maximum value for among all of these subarrays. So maximum value for among all these subarrays simply mean that you don't actually have to go through like each subarray. Sum of ij is simply sum of I to j. This is constant and it only depends on x. So try to find an x for which the sum is minimum. Like this is eventually the sum is, this sum is the sum of maximum subarray only. Absolute sum, absolute maximum sum of subarray. This is that thing. This is not for one. If you're like considering this for just for ij, I have not decided the ij here, right? And why can I do this? Why can I do this? Because eventually ij, see, if these two things would have been different, then I couldn't have been like, I could have done this. But these things are constant for both, right? So they only depend on x. Other thing is just constant. I can write this as c minus kx and this as kx minus c. So this c is a constant. This only affects, like if you draw for different c's, how will it change? It will make the like the line go up down, right? Just right. And the other line will go up down. But the maximum value, like the maximum value will always be like the upper graph, these limits only, right? This thing for the complete array, like for the complete array, if you find the poorness, you'll get the value among these lines only. If for x, this value is also there, this value is also there, this value is for different ij, this value is for different ij, and this value is for also one ij, but this is the maximum out of those. So do you get it? Like okay, finally, if you want to see the graph, it will actually look like this. For one ij, it will be like this. For another ij, okay, this is okay. My screen is visible.
Yes.
Yeah, I think this has frozen. Okay, if you want to really imagine how the graph will eventually look like, it will be something like, okay, where did I draw that? Let me erase this here. It will be something like this. The screen is freezing a lot. So the final graph will look something like this. Like they will have different slopes and something maybe like this. So eventually the final graph will look something like this. Like these are the values that are maximum, but this is also kind of v only, right? So this is the value of x that you have to find. Do you get it now? But you don't actually have to like look at this. If you are comfortable with this understanding that we have a v, it's more than enough, and we have to find.
I got it. The second one.
But for everybody else, like this is more than enough. If you get this intuition that we are getting a v and we have to find the minimum of that v. So is it okay for everyone?
Hello.
Yes, yes, yes.
Yeah, like for different ij, there can be different x points, right? Like there can be different minimum points. So in that case,
no. Like I again said, like there you're talking about this, right? Minimum different, like this, right?
yes,
Right.
yes.
This is for one.
Yes.
So if you take the maximum out of this, you again get a v only. Like the thing that you get is this thing. You'll get this thing. That is this. You'll get this as your function. This is like you'll eventually get v only. So that's why I didn't want to get into these kind of graphs. Like eventually it will be kind of v. So you can assume that you have to find this minimum. Is it okay? Like, this is the graph that you get. So this is the graph. So how to find this? Like I said, we can apply ternary search. So now things that we have to look for is, first of all, the range that is given to us. Like it's in order of, initially I think it is in order of 10 to the power 5 or okay, it's 10 to the power 5, 10 to the power 4. And x can be in range from like low is from 10 to the power minus 4 to 10 to the power plus 4. So first of all, you'll have to take care of low also. X can be negative also, right? Then since this is working with precisions, and like I said, it's better when you're working with precision problems, it's better that instead, like you can have this like this also, while high minus low is more than or equals to 10 to the power 10 to the power what? 10 to the power minus 6, right? But tell me one thing. We are applying binary search on high minus low, but finally we want our answer close, like the value should be close to this, right? So don't do this thing. If you, like I said, in this problem, if you like try solving this problem using this once, maybe you'll get a wrong answer. Why? Because the same, like I said, precision, you get sometimes precision error because of when you use while loop. So what I have done in my solution, give me a second, my screen has frozen. Audible, right?
Yes,
So is it always like that? Whenever we have a problem in where it is mentioned error, we'll
Yes.
use a for loop,
Like okay,
that iteration part.
if you always use for loop, like you won't get wrong answer. But sometimes like it's not always necessary that like like in some problems it's required to use for loop only, but while loop will also work in some problems. But if you're using while loop only, then in some problems you'll get wrong answer, like in this problem. But if you're using for loop for like the problems which are having decimals and you're applying binary search and you're using for loop, so it always guarantees that you are going up till that precision level. So in this problem, I'm iterating for 100 times. So the precision will finally for x will be 2 to the power 100. Like the range will be finally will get divided by this factor. So I'm guaranteeing that my final answer is at least 10, like having a precision of 10 to the power minus 6. So what I'm doing, I'm having a low value, I'm having a high value, then I'm iterating in my for loop 100 times, I'm iterating 100 times, and I'm doing the same thing. What does I'm calculating mid 1, mid 2. If the value at mid 1 turns out to be more than the value at mid 2, I'll change my low to mid 1. Otherwise, else I'll change my mid 2 to mid 2 to I'll change my high to mid 2. Is it okay? Is it okay? Yes, no, anything? Yes. Okay, so I'll show you the implementation. So this is the implementation. In this, I'm first taking n as input, then I'm taking array a as input. Then this is my low value. Like I said, in some problems, you don't actually have to blindly like just take low as 0. So in this, it is 10,000 and high is also 10,000. Why? Because the array values are itself in this order. If you decrease the values more than this, like if you take x outside this range, it's of no use, because the values will eventually be, each value will either turn out to be more than 0 or less than 0. See, if you look at the problem statement, the values in the array are in this range. The absolute value is between, like it's less than 10,000. So the values are between minus 10,000 to 10,000. So now if my low is up till this, R is up till this, now B is nothing but B is a new array that I'm creating. So you don't actually have to do this, but like first I'm taking the value as B of I is A of I minus mid. For each value, this is this. Okay. Now I'm calculating the maximum of this, the maximum that I can get from this function. And then the other function is mid minus AI. And then I'm taking the maximum of any, like this is greedy, like how to calculate the maximum sum of any. See, I have two functions, right? The first function is like this, and the second function is like this. So I'm calculating the maximum sum that I can get for this function also and this function also. And how do we get, like what is the algorithm's name if you want to find the maximum subarray sum? Cadence algorithm. Yes. So this is cadence algorithm, if you'll remember. So like sum plus bi, if sum is less than 0, make sum 0. Otherwise, x is equals to maximum of x comma sum. So x here is nothing but the maximum, like the value at this mid, and y is at mid 2. So once is from this function and second is from this function. Now I'll take, like here I'm taking answer as maximum of these two, because finally you'll have to answer your value as x. Like in the problem statement, you have to find the real number x, okay, such that the weakness of like this value of x you have to find. So if x is, like I said, if x is more than y, I'll change my left to this part. I'll bring my this low to this mid. Otherwise, if my r is more than, like if y is, this thing is more than this, bring my r to mid. So instead, like this would have been, like I could show you using mid 1 and mid 2 also, but this is also the same thing. But let's say if I want to do this using mid 1 and mid 2, how to do this using mid 1 and mid 2? So I'll have one mid 1 and one mid 2. So this is L plus r minus L by 3 like the earlier thing is also the same, but I'm using that for two functions, right? And this is using this thing. So now x is the value that is at this mid one. How to calculate this? Mid one, I'll calculate my x, and at mid two, I'll calculate my y. Once this is done, if x, I can shift it to mid one, otherwise to mid two. Is it okay? Is it okay? Yes, no, anything? Yes, k less than 60 will also work. Like you'll have to check it once. I haven't really submitted it k less than 60. I have submitted for 100 only, but I think it should work. Is it okay? So you see for ternary search problems, you'll have to first connect, like you'll have to find on which thing you'll apply ternary search on. Like you'll have to draw the function, and then you'll see on what thing, like how to apply ternary search. And in case you're having these kinds of errors, if you try to submit using that, like using simple error, you might not get precision error. Like your answer will be close to the answer, but it won't be exactly same. So you'll get wrong answer. So in order to avoid that, it's recommended to use this for loop 100 times, because the time complexity is still same, right? Earlier it would have been some 32 times, let's say n, now it's 100 times n. So that's why it's better to use this for loop in these cases when you have error. So I think it's already 2, and that's it. So if anyone is having any doubt, you can ask me right now, otherwise we'll stop. And by the way, I'm going to share that feedback form right now. Yes, I have shared the feedback form in the announcement section, so kindly do fill it. So yes, interactive problem code, I'll give you that also. Just give me a minute. Provide you it in the chat. Just give me a second.
No, Bhaiya,
Yes.
where can you once more explain the ternary search, how high and low is being shifted to mid one and mid two? Mid two. I am getting confused.
Okay, I'll just give you. Just give me a minute, okay? Okay. So interactive problem, the ask thing. I will share the ask thing and this thing in the chat. So I shared the interactive, like this is my template, this is what I use. I've shared it in the chat. And now the doubt that is, see, if you have a V, or like if you don't have a monotonic function, it is increasing and then decreasing. So like this, and this is low, this is high, and you have to find the maximum. Then let's say this is your mid one, this is your mid two. So you always shift to that place. See, if M1, if the value at M1 is more than M2, then you change your low to mid one. That is, bring this position to this. And if otherwise, you'll change your high to M2. That is if you had something like this. Okay, in this case, if M1 is less than M2, I'm sorry. If M1 is less than M2, then this thing. Otherwise, if let's say I had something like this, M1 is this, and M1 is this, M2 is this. So if M2 turns out to be less than M1, the value at M1 turns out to be less than the value at, just give me a minute. The value at M2 turns out to be less than the value at M1, then you'll shift your high to M2. So just remember, when you're trying to find the maximum in your, so when you're trying to find the maximum of your parabola, then if you have two things, M1 and M2, mid 1 and mid 2, then you'll shift your low or high, that is the boundary, to the value which is having a lower value. Well, if M1 is having lower, you'll shift to lower value. If you're trying to find the minimum of your parabola, then if you have mid 1 and mid 2, you'll shift your boundary to the value which is having more value. So you always shift your boundary to the opposite value. Is it okay now?
Yes, Bhaiya.
And yes, like this is only maths only. Like ternary search, if you like come to ternary search, you'll first have to write equations, then you'll have to apply ternary search on that thing. And the problems that you can, usually the problems are in range of 1900 plus. Like I don't think there are problems that are less than 1900 rated for ternary search. But anyway, interactive problems are also up to, like, they start from 1700, 1800 range. But if you're if you know these topics, you'll find that you can easily solve these problems. So if that's it, no other questions are, we can stop the meet. Okay, so thanks for joining. Bye bye, and kindly fill the feedback form too.